Good evening, ladies and gentlemen. My name is Howard Burton, Executive Director of Perimeter Institute, and it gives me great pleasure to welcome you back here for the first public lecture of 2007. We have a real treat for you this evening. Professor Nima Arkani-Hamed of Harvard University is widely recognized as one of the most creative and original physicists of his generation. Professor Arkani-Hamed actually grew up in the Toronto area, and I'm going to make a little aside from my usual introduction because we have a special treat to show you that we are the Physics Institute with a heart. We have arranged for a special VIP gentleman in the front row, Mr. Charles Ledger, who was Nima's grade 8 mathematics teacher. To be here this evening, and it is really wonderful. I'm sure everybody appreciates this, and certainly every physicist at Perimeter Institute or anywhere has had at least one transformative experience with a high school or junior high school teacher that has played a tremendous role in setting them on the path to professional science. And Mr. Ledger has clearly done that for Nima, and they had a wonderful, wonderful reunion earlier this evening. So just like to point that out, and now I'm going to go back to the standard aspect of the introduction. So from Zion Heights Junior High, Nima then moved on eventually to the University of Toronto, where he did an undergraduate degree in mathematics and physics. And from there, he moved to Berkeley, where he did his PhD. After that, he did a postdoctoral fellowship at SLAC, the Stanford Linear Accelerator, and then returned to Berkeley for a professorship before moving on to Harvard University, where he became a tenured full professor at the precocious age of 30. Professor Arkani-Hamed has made many seminal developments in the theoretical physics world. He's known for somebody with a tremendous amount of energy and passion and creativity. He has led developments in such exciting and seemingly arcane topics as large extra dimensions, as little Higgs theories, split supersymmetry. Nima's almost always on the forefront of developments, never resting, never content to merely work out all of the details of his provocative developments, but pushing onwards, trying to understand, trying to get a deeper understanding of reality. He is an exciting person, a dynamic lecturer, as you will find out. His accomplishments have also been recognized in a more popular venue. In 2000, he was recognized as one of the top 20 young scientists to watch by Discover magazine. Most recently, he was recognized as one of the Brilliant 10 by Popular Science. Of course, the bar keeps going up, so I'm anticipating that in the coming years, we will hear of Nima being recognized as one of the Fabulous 5, one of the Thrilling 3, and culminating, of course, in the Omnipresent 1. Ladies and gentlemen, Nima Arkani-Hamed.
Just me. Thank you. And I have to, now someone explained to me 10 times what to do here. So let's see, did I do it right? All right, excellent. It's an absolute pleasure to be here. Thank you, Howard, for the introduction. I'll have to kill you later. But thank you very much for the wonderful introduction. What I want to talk about, this title is slightly different than the advertised one, but the content is the same, is the future of fundamental physics. And I realize this is a rather modest title, but I'm going to confine myself to talking about the future on the time scale of, let's say, the next 5 years or so, or what we might know by 2010. Last year, I gave a talk at the Perimeter Institute at the conclusion of a conference on what physics would look like in 2050, and I'm not bound to make that mistake again. So one of the most interesting things about our subject, especially in theoretical physics, is that theoretical physics really thrives on crises and on paradoxes. You know, most people don't like crises or paradoxes, but theoretical physicists love them. And we love them because when there aren't crises and paradoxes, someone else has understood something. It's nothing for you to do. But anyway, that's happily not our situation today. The subject is filled with crises and paradoxes. And in fact, many of us feel that the current struggles in the subject are paving the way for a real revolution in our understanding of physics, perhaps on the same scale as those of relativity and quantum mechanics at the beginning of the 20th century. That's purely from a theoretical point of view. There are a lot of mysteries and paradoxes that we've been struggling to understand. But what makes this talk timely, and such talks in general interesting today, now, is a spectacular new experiment. I'm a theorist, but our experimental colleagues have been working to perform miracles. And the fruits of their labors are culminating in an amazing new experiment called the Large Hadron Collider, which might well usher in the revolution that I'm talking about. And what's exciting is that this experiment is finally starting this year. This September, this accelerator turns on. People have been waiting for this experiment for over 20 years, so we're very lucky to be living in the epoch where it's beginning to turn on. So this is what the Large Hadron Collider looks like. In the distance there are the Swiss-French Alps. And of course, this is an aerial shot. From the air, you don't see a giant red oval on the ground. The giant red oval, underneath that giant red oval, is a beam. And protons, which are one of the constituents of the nucleus, one set of protons rush around clockwise around the ring, another set of protons rush around counterclockwise around the ring, and at a number of places around the ring, they're made to smash into each other head on. And something interesting happens. This ring is around 28 kilometers around, to give you an idea of scale, and it straddles the Swiss-French border. Okay. Now, as I said, I'm a theorist, so you're going to be seeing few pretty pictures in the talk. Instead, you're going to be seeing ugly pictures. But anyway, this is what is going on. As I mentioned, we take 2 protons. There's proton number 1, proton number 2. And they're each accelerated to very, very fast velocities. So each one is accelerated to around 0.999 the speed of light. Okay? So there's proton 1, proton 2. For some orientation, the proton is around 10 to the minus 14 centimeters big. Okay? So that's about 10 to the minus 14 centimeters big. Throughout the talk, you'll be seeing this little graphic. I'm a horrible artist, so this little graphic, just remember, is a magnifying glass. Okay? So I take the magnifying glass, just to tell you, when I look at the proton in the magnifying glass, well, first, paradoxically, it shrinks. But anyway, ignoring that, you see that the proton is made up out of more elementary constituents called quarks. So the proton is made out of 2 up quarks and a down quark, as well as a bunch of stuff that glues them together and keeps them in a bag. The proton is like a bag that's made out of quarks, and the things that hold them together are imaginatively called gluons. So the proton is made out of quarks and gluons. And really what's going on when we accelerate the proton to 0.99 c is that these constituents are also moving really, really fast. The constituents don't, as far as we know, have extra substructure. So when they smash into each other, something interesting happens. That something interesting is represented here as pow, okay? And when we accelerate things to these very, very high velocities, the distances that we get to probe at these very high velocities is around 10 to the minus 17 centimeters. So that's about a factor of 1,000 smaller still than the proton itself. Just to give you an idea, in the entire period of development of experimental particle physics from, let's say, 1945 to the late 70s, we managed to cover a set of distances between around 10 to the minus 14 centimeters and 10 to the minus 16 centimeters. Okay? So every factor of 10 hurts. And so this extra factor of 10, the shortest distances we've seen today being around 10 to the minus 16 centimeters, it's taken us around 30 years experimentally to figure out how to go from 10 to the minus 16 to 10 to the minus 17 centimeters. Okay? And by the end of the talk, if you're not all abuzz about why 10 to the minus 17 centimeters is so exciting, I'll have failed miserably. Okay? But what actually happens is, unfortunately, not a big fireball pow. When we smash into each other these very high energies, we probe very short distances, new things happen. Often, the study of particle physics is characterized as caring about what the ultimate building blocks of matter are, or finding new particles that we can give silly names to. But it's really not the particles we care about at all. What we care about is the structure of the underlying laws that govern them. And we've learned over 400 years of experience in fundamental physics that the structure of those laws, their properties, their simplicity, and their surprising features manifest themselves most cleanly, most transparently, most beautifully at short distances, which is why we explore physics at short distances. But the way that those new laws show up does tend to be in the form of new particles. So we're going to make a lot of new particles here. However, those new particles don't come out with little name tags that say, I'm a new particle. They very quickly decay in a time of around 10 to the minus 27 seconds, which is about the time light takes to traverse 10 to the minus 17 centimeters. And around that time, they decay back to ordinary particles. Here's an electron, there's an anti-electron or a positron, there's a quark, there's a muon. And we have to tease out from this structure of what comes out what it was that went on in that POW region. Okay? Now, to give you an idea that there are serious people who work on this subject, quite ironically, despite the fact that we're looking to understand these really, really tiny distances, what we have to do to capture the debris of these complicated collisions just requires extraordinary engineering and technological virtuosity. Okay? So the detectors that have been built to see the debris of these collisions are the most complex and interesting objects of their kind ever built. Here is an example of one of the detectors, one of the two detectors that's going to see this debris. It's called the Atlas detector. This is something like 30 meters high. Okay? It's something like 40 meters deep. Everything about this experiment has the word biggest, largest, extreme, extreme. Okay, so let me just give you some of them. It's the largest experiment in human history. 2,000 people work on it. Okay? For example, another random example, the cavern that they had to dig out for this detector. This is underground, many meters. It's the biggest cavern that's ever been built. Okay? The cranes that they have to use to move these things around are the biggest cranes there are. They like move, whatever is bigger than a 747. They like pick them up and move it. It's the same kind of stuff that you need to move things around. And I'm not even going to, it would be an entire talk in itself to even talk about what's going in here. I just want to emphasize, this is all built in order to capture every last bit of information that we can get out of the debris of these very violent collisions. So in this picture, one of the proton beams would be coming in this direction, another proton beam in the opposite direction, and they smash into each other somewhere in the middle of that monster. Okay, but since I'm a theorist, I can show you pictures like this. Okay. Sorry, this is continually getting cut off here, but that's fine. So I want to just give you some context. I want to give you some context for what I'm talking about. As we understand it today, all the interactions we know of are gravity and electromagnetism, which you're familiar with from high school, as well as less familiar interactions that operate at much smaller scales in the atomic nucleus, the weak and the strong nuclear interactions. The weak interaction isn't like a push or pull force. It makes a neutron decay into a proton, an electron, and something else called a neutrino. That's ultimately what's responsible for radioactivity, while the strong interaction is what, for example, keeps the two protons and neutrons inside the helium nucleus. You'll remember those protons are both positively charged, so they want to be repelling each other like crazy, but they don't. And the reason is that there's actually much, much stronger force still than electromagnetism operating between them, and that's called the strong nuclear force. So those are the interactions. Those are the fundamental interactions. And I also want to give you a sense of the various distance scales we're familiar with in nature. Starting at the biggest distances is around 10 to the 28 centimeters. People always ask me why, when it's so big, I use centimeters, and I just don't have a good answer to that question. I just like centimeters. But anyway, at the largest distances is around 10 to the 28 centimeters. That's how long, that's the distance light travels in around 10 billion years, and 10 billion years is about the age of the universe. And as we go to shorter distances, something interesting happens almost every distance of 10 as you go down. For example, about 1 million times smaller in the universe, we have galaxies. We hop a large distance again. The solar system is around 10 to the 14 centimeters big. Me is 10 to the 2 centimeters big. I'm not too good with factors of 2, okay? If we go to still smaller distances, there's a DNA, maybe 1/10 of a micron. Atoms are around 10 to the minus 8 centimeter big. And as we continue this march, the nucleus of the atom, the protons and the neutrons, is around 10 to the minus 14 centimeters. But I've highlighted two scales. One of them was the largest scale, and the other one is this 10 to the minus 17 centimeter scale, which has a name. It's called the weak length. Okay? Now, that's where the LHC is going to go. That's the height of my technological sophistication. I'll make up for it in other ways. Okay. Now I want to show you the same picture of scales, but more from the point of view of a fundamental physicist. Okay? So here they are again. I hope they all fit. There, they kind of fit. Okay. Oh, no. Okay, I'll be doing this a lot. Sorry. So again, we have the scales that I told you about. Now we add an element of surprise. So the entire previous transparency was between there and there. There's actually a third important scale, around 10 to the minus 33 centimeters. This is called the Planck length. Okay? And we'll talk about its significance in a moment. Now, sorry? Oh, you can flip it. Oh, brilliant. Excellent. Sorry. Uno momenti. Wait. Oh, yeah. Cool. Now you're going to force me to rotate by 90 degrees left or right throughout the rest of the talk. And that's all right. Okay. So there are the much more clearly presented three fundamental scales of physics. And each one of these scales is associated with one of the crises and paradoxes I was talking about. Okay? So at the shortest distances, the 10 to the minus 33 centimeter scale is associated with the problems of quantum gravity, and really with the fact that we know that one of the most basic properties and things in physics, the idea of space-time, really fundamentally doesn't make sense and has got to emerge from something else. This is the purview of subjects like string theory, and it's become fairly clear that string theory, whatever it is, can't be the final word on the subject, so it's really string theory and beyond. But that's one set of crises. Another set of crises have a rather different character. Okay? the set of crises have to do with one of the most salient properties of this picture, which is that there are three very, very different scales from each other. This Planck length is much, much larger than the weak length is much, much larger than the size of the universe. As we'll see, this is a very crucial and basic property of the universe. But as we'll also see, understanding this large separation between these distance scales is very, very mysterious. So understanding why the weak length is much, much larger than the Planck length poses a major puzzle. Understanding why the universe is much, much larger than the Planck length poses a much, much more severe major puzzle. But they both have the same basic character. As we'll see, they're known as fine-tuning problems. And one way or another, they have to do with taming the quantum vacuum. And this will make more sense to you as we proceed. But I just wanted to show you that there are three very basic scales. Most of us who think about this, most of us who work in this business, bop around between them daily. The problems I told you are at some level interrelated. But I just wanted you to see that they're at least simple to characterize, and you'll understand them more as we proceed. OK. So what I want to spend the talk doing then is first to quickly review how we got here, talk about where we might go, and with telling you what the LHC can tell us about these problems. OK, so first, how do we get here? Well, a persistent theme in all of modern physics, really the beginning of modern physics starts with Isaac Newton's realization that two very different seeming phenomenon, the apple falling on his head by the gravity of the Earth and the moon going around the Earth, are actually caused by exactly the same agent, the universal law of gravitation. That's not at all obvious. We teach it in kindergarten now. But it's maybe a little after kindergarten, but it's not at all obvious. And it was one of Newton's several feats of genius of realizing that this is so. Very different seeming things are actually caused by the same agent. This continued in the 1800s. It was realized that still very different seeming things, like electricity and magnetism, which were known to the ancients, thunder, lodestone, lightning, lodestone, they seem to have nothing to do with each other. They're in fact different aspects of exactly the same thing. And in all of these cases, when seemingly very different phenomena were unified, something interesting happened. Not only did you get a uniform understanding of a bunch of different phenomena, you also got a surprising set of new phenomena that you didn't even know to expect. So for example, the ideas of gravitation led not only to an understanding of why the moon went around the Earth, but also how the Earth went around the sun, and comets, which were the total which stuck out, no one could explain before. The unification of electricity and magnetism led to the realization that light, which doesn't itself seem to have anything to do with either one, is actually made of undulations of electric and magnetic fields. The period 1900 to 1930 brought even more profound insights, those of special and general relativity, and the even more radical ideas of quantum mechanics. And there'll be a few equations in this talk. You don't need to understand any of them. And I'll actually go through this part rather quickly. But in special relativity, space and time were unified. Two different things. They became unified and were seen to be part of the same basic thing, space-time, so that just as ordinary spatial dimensions could be rotated into each other, we could somehow rotate space and time into each other. And that there was just with a simple minus sign, a generalization of the Pythagorean theorem that told you how to make sense of lengths, not in space, but in space-time. So energy and mass were unified. You've all seen equals mc squared. Later, in general relativity, it was realized that one of the things that was taken for granted as being just the static arena in which physics happened, space and time, or now space-time, was itself dynamical. And that we could think of gravity as being due to the curvature in space and time. Again, this idea that space-time could be curved led to a qualitatively new sort of prediction. Once space-time isn't static, but can respond to the presence of mass and can change itself, new sorts of ideas become possible. The language for new sorts of ideas become possible. The idea the universe is expanding, for example, is an immediate consequence of general relativity. You can't even talk about it in a meaningful way without the idea that space and time aren't static. When we say the universe expands, it doesn't expand into anything. What happens if there's two galaxies, and as the universe expands, the distance between them increases? What that means is that there's more and more space being created between them. They're not expanding into anything. You can't even talk about this without a language in which space and time aren't static. That's, of course, a prediction that was spectacularly borne out by experiment. Black holes are another consequence. Black holes are another consequence of the curvature of space and time, where space-time can get so curved that even light can't make it out of a region of sufficiently high mass in a sufficiently small radius. Is there some way we can flip it back around? Do I just press a button? Image rotation. Should I even press anything? Oh, that one. Okay. Oh, gosh, I should do it again. Oh, okay, every time I do it, it flips again. Oh. Once more. There we go. All right, excellent. I'm good. Quantum mechanics continued this. Quantum mechanics continued this trend. What were thought of as being waves and particles in a classical description of the world were, again, seem to be different aspects of the same thing. There's no such thing as waves at all at a fundamental level in our description of nature. Instead, everything's a particle, but it's a quantum mechanical particle. Sometimes quantum particles behave as classical waves. Sometimes they look like classical particles, but really everything's a quantum mechanical particle. And the reason it was so radical is it was associated with this amazing shock of the failure of the classical idea of determinism, that you could predict the future if you specified the positions and velocities of all particles at a given time. You could predict everything about the future. The very words about what physics was even supposed to be about, which was predicting the positions and velocities of particles in the future. That's what physics was about. The very words were lost with quantum mechanics when we realized that the sentence positions and velocities doesn't make any sense. There is no such thing as position and velocity of a particle. And this is famously encapsulated in the Heisenberg uncertainty principle that says that if you know better and better where a particle is, you know worse and worse what direction it's moving in and what its momentum is. And similarly, if you know better and better what time some set of events took place in, you know less and less what energy they have. Okay? Again, this unification predicted new things. In this case, for instance, there was the bizarre ideas of quantum mechanical tunneling. If this is a little hill and there's a ball sitting there, in a classical world, the ball will just sit there forever. In a quantum mechanical world, I can't know that the ball is actually at the bottom of the hill and not moving at the same time. So there's always some chance that it's either not really at the bottom of the hill, or it's at the bottom of the hill and it's got a big enough velocity for it to be able to get through. So that means in a quantum world, there's always some tiny, tiny probability that I'll spontaneously appear on the other side of that wall. For me, that probability is 10 to the minus 10 to the 30. It's safely small, okay? But for much smaller objects, it's large. In fact, this bizarre quantum phenomenon is what's responsible for currents in metals. It's what's responsible for semiconductors working. It's what's responsible for transistors working. It's therefore at the basis of all of modern electronics. Okay? So this abstruse fact about the uncertainty principle is of crucial importance for things in our everyday world. In fact, in a more amazing way, the uncertainty principle and the ideas of quantum mechanics, unlike what you read in many new agey popular books on the subject, far from making everything fuzzy and uncertain, are responsible for the very stability of all matter. Okay? The reason why the electron that's orbiting around a proton in an atom, well, why the heck doesn't it just fall down into the proton? In a classical world, it would fall down into the proton. In a quantum world, it can't, because again, we can't know that it's both sitting on the proton and it's standing still. Okay? And it's the uncertainty principle that's ironically directly responsible for stability and the fact that that the world around us has any solidity to it at all. So those ideas were set by the late 30s, and much of the rest of the 20th century was occupied with a synthesis of the ideas of special relativity and quantum mechanics. Now, these two important new frameworks were synthesized together in something called quantum field theory. And this again, this unification, again implied bizarre, exciting new phenomenon that were totally unanticipated. For example, putting special relativity and quantum mechanics together forced the doubling of the world. It forced the existence of antimatter. You've all heard of antimatter. Every particle, like the electron, has a partner, an antimatter partner called the positron with opposite charge. These guys wouldn't want to meet each other if they each wanted to have a chance of survival. Okay? And the proton, for example, has an antimatter partner called the antiproton. So it's amazing that the unification of space and time and quantum mechanics doubled the world. It doubled the number of kinds of things there were in the world. And this is an immediate prediction of the combination of special relativity and quantum mechanics. It's such a shocking prediction that the theorists who originally made it didn't want to make it. It seemed too crazy to be true. And eventually they were forced, often when you're on the right track in theoretical physics, the theory is smarter than you are. So the theory kept saying, no, sorry, you can't hide me, you can't get rid of me, I'm there. They finally bit the bullet and said, okay, I guess the world is doubled. And fortunately, nature agreed in a few years, and antimatter was discovered. I just want to give you a flavor for how this happens. Why antimatter has to exist. Oh, this one I won't bother with. Here I've drawn a picture. The vertical axis is time, the horizontal axis is space. And something that many of you have learned in high school is that relativity tells us that nothing can go faster than light. The argument for that is that if I have an event A and another event B, and let's say from A I send an electron to B, I've drawn it so that the electron is getting to B faster than light would allow it to do so. And the argument is that if another observer were to view exactly the same sequence of events, another observer moving at constant velocity, they would see the time ordering of B and A reversed. So it seemed that causality is totally violated. If it wasn't sending an electron from A to B, but me picking up a gun and shooting someone, then some other observer would see the second person bite the bullet, as it were, before I fired the gun. Okay? And that's completely in contradiction with the normal laws of causality. But there's another possible interpretation when it's just an electron being sent from A to B, which is that, well, maybe something is just moving forward in time from B to A, but whatever it is, it has to have exactly the opposite charge as the electron. So either causality is wrong, or there must exist a new kind of particle. And of course, nature chooses causality not to be wrong, and forces the existence of a new kind of particle, the anti-electron. The existence of antimatter forever changed our notion of a vacuum. Remember, I just told you in general relativity, space and time were made to be dynamical. In quantum mechanics, if we add quantum mechanics now to the mix, quantum mechanics and just special relativity further make even the vacuum dynamical. I mean, you might think that such a basic notion as vacuum, nothing, emptiness, would be well defined. There would be such a thing as vacuum. Well, there isn't really. And here's a simple reason. Let's say I try to check that this region of space is empty. Well, how would I do it? I have to take one of my famous magnifying glasses and look at that region of space. Well, if I'm trying to look in a small region of space, I have to, by the uncertainty principle, put a lot of energy into that region. But because there are antiparticles, if I put enough energy into that region, the energy is allowed and possible to create a particle and an antiparticle pair. So how do I know when I was looking that it was empty and I made it by the act of looking, or there was something there to begin with? You don't know. There's no operational way of verifying that some region of space is empty. There's no such thing as the vacuum. The vacuum, when you have quantum mechanics and special relativity, is a very interesting, complicated place. There are constantly particle-antiparticle pairs popping in and out of existence all the time. And if you look with a powerful enough magnifying glass, even at vacuum, you'll see them. This is another, again, remarkable prediction of a simple ideas of a simple unification between special relativity and quantum mechanics. And these fluctuations of the vacuum actually solved a very old conundrum of classical physics. One of the major mysteries in classical physics around 1900 was that people thought the electron was point-like, had no substructure. And so you may remember that there's an electric field that surrounds an electron, and that electric field gets stronger and stronger the closer and closer you get to the electron. Well, that electric field has energy in it, and because that electron is an exact point, the classical physicists calculated the energy stored in that electric field, and they got the answer infinity. That doesn't make any sense. Okay. We're going to run into this sort of problem again. That didn't make any sense at all. And so what did they do? Well, they did the best they could. They say, well, maybe the electron isn't a point, maybe it's a little bag, maybe it has some size. None of these things worked. None of them worked because it was the wrong answer. The right answer had to await 40 years, the development of quantum mechanics and special relativity. That told us, actually, there's no such thing as a vacuum around there. As you get closer to the electron, you start seeing that there's just popping out of the vacuum constantly electrons and positrons, electrons and positrons. So which one is the electron? Is it that one, or is it one of these electrons, or that one, or that one? You don't know where it is. You don't know where the electron is. It's always surrounded by this cloud of particle-antiparticle pair. So you can't actually localize exactly where the electron is. And because of that, there isn't this infinite energy. Okay? The infinite energy gets screened by the presence of these electron and positron pairs. So I've told you a lot of basic physics, basic 20th century physics. And these developments culminated in the 1970s into a theory known as the standard model of all interactions. This theory is spectacularly successful at describing everything at distances bigger than around 10 to the minus 16 centimeters. No experiment contradicts it. Even at precisions approaching 1 part in 1,000, there are hundreds, maybe by now thousands, of different sorts of experiments, different observations, where the theory makes a prediction, experiments are done, and within the accuracy both of the prediction of the theory and of the experiment, they match. And that accuracy approaches 1 part in 1,000. There are some things for which this precision approaches around 1 part in 10 to the 12. That means there are some quantities that agree between theory and experiment to 12 decimal places. Well, some quantities, this quantity. Okay? This is one of the most beautiful things in all of science. The electron, our friend, has a very simple property. It has a spin. Okay? The electron is like a little magnet. In fact, this is why magnets are magnets. They're made out of electrons, and each little electron individually is a little magnet. It's like a little top that's spinning. And there's a number that characterizes the strength of that magnetic force. It's called G. Never mind why it's called G. But anyway, it's something that's been by now measured to extraordinary precision by experiments. So here's the experimental value for this G quantity. It's 2.002319304337. Of course, this is physics, so there's an error bar. Plus or minus 0.000, I'm getting bored. Okay? All right. Now there's a theory. The standard model also has a prediction for this number, which is, as I've shown. Okay? And we don't have to count how many decimal places they agree to. This is the most stunning agreement between theory and experiment ever in science. And it's a reflection of the precision of the theory we have at our disposal. The standard model is a unified theory of all the interactions in a deeper and more profound sense than you read about speculative unified theories in the popular press. The standard model taught us that the huge apparent disparity between electromagnetism, the strong and the weak interactions, is a long-distance illusion. And that really at around 10 to the minus 16 centimeters, as I promised you, when you go to short distances, the essential simplicity of the laws show up, and their similarity shows up. And we understand that these very different seeming things actually have a very similar description. Not identical, but very similar description. This would be a topic for a whole talk in itself, but we understand that the electric force, electromagnetism, is associated with the interactions of electrons and photons. that the strong force is associated with interactions between quarks and gluons that I talked about earlier. Very similar sorts of pictures, very similar sorts of equations, very similar sorts of ideas. So there's a unification at a profound sense at the level of the ideas we use to describe these interactions. And the weak interactions are associated with, again, a very, very similar sort of picture. There is one missing piece of the standard model that's yet to be verified that has to do with the origin of mass. Remember, I told you this is a theory for everything at distances bigger than 10 to the minus 16 centimeters. Well, one of the things, everything has mass, right? So if you have a theory of everything at large distances, it should also be a theory of mass. And it does give you a theory for why things have mass. I can at least give you a cartoon of it by saying that we understand that all the particles that have mass of a certain type get it because the universe is actually filled with a certain sort of condensate. Think of it as being filled with a fluid, although it's not a fluid like the old luminiferous ether was a fluid. It's a more interesting kind of fluid than that. But it's filled with a fluid. And for example, the electron, as it's wandering through space, every now and then bumps into this fluid. And its bumping into this fluid is what's responsible for its inertia. Now, the electron happens not to bump into it with such a big strength, so the mass of the electron isn't all that big. Another particle that does interact with this fluid a lot is called the top quark, and so it has a very big mass. The photon, for very good reasons, doesn't bang into it at all, so it's exactly massless. But the important point is that the typical length scale between these interactions, between these collisions, is around 10 to the minus 17 centimeters. Okay? That's an actual scale in physics. It's one of the important parameters of this theory. There's a meaningful number, 10 to the minus 17 centimeters, which is that every single thing around gets mass because it bangs into something every 10 to the minus 17 centimeters or so. Okay? Now, I told you about this sort of quiescent fluid, but you should then not find it surprising that if you then bang things into each other at distances approaching 10 to the minus 17 centimeters, you might be able to make a little ripple on this fluid. You might be able to excite this fluid in some way. And that little ripple will show up in the accelerator as a particle. That particle is called the Higgs particle. And it's, as I said, the last missing piece that hasn't been verified in the standard model. We all expect, with very high, I've bet months of salary on it, that the Higgs particle will be found at the Large Hadron Collider. And we should have concrete evidence for it by 2010. So whatever else I tell you about in the rest of the talk, this is one thing we should for sure expect to see at the LHC, the last piece of the standard model. OK. So far, I've told you a very rosy story. Everything's great, 12 decimal places, blah, blah, blah. Right? So why am I giving this talk? What are the crises? All right. Let's start at the top. Let's start at the crisis at the shortest distance scales. Okay. It's the idea of emergent space-time. And this is beautiful because it's one of the deepest mysteries in physics, and it's one of the easiest to explain. Okay. Remember, we said that if we want to probe shorter and shorter distances, we need higher and higher energies. That's because of the uncertainty principle. So that's why we have to beg governments for lots of money to go to higher and higher energies to explore shorter and shorter distances. OK. So, but OK, apart from the fact that it costs a lot of money and people are reluctant, in principle, you could think you could keep doing this forever, right? Let's say you want to go to even shorter distances. Well, you ask for more money, you build a bigger accelerator, you smash things into each other at even higher energies, you probe shorter distances. The fascinating thing is that at some point, this process stops. And it stops when the following bad thing happens. Okay? So suppose that you want to see what's going on in this tiny region of space, so you need an amount of energy that goes like Planck's constant divided by the amount of time that you're looking at. OK, but you see what's happening, right? As you want to go to shorter and shorter times, you need bigger and bigger energies. At some point, you're putting an awful lot of energy into an awfully tiny amount of space. You're going to put so much energy into that tiny region of space that now, because the world also has gravity, that region of space collapses into a black hole. Okay? That sucks. Now, you put in the numbers, and this happens when the times are around 10 to the minus 43 seconds. The distance is around 10 to the minus 33 centimeters. The fact that those distances are so small is a reflection of how weak gravity is. Okay? But still, you go to tiny enough distances, it collapses into a black hole. So you can't see what's going on in there. What if you say, damn, I'll just ask for more money and build an even bigger accelerator and smash things into each other even harder? What happens then? Just make a bigger black hole. Okay? That means that there's no operational way of measuring distances in time smaller than 10 to the minus 33 centimeters. Okay? Every single time this has happened to us in physics before, where there are some quantities we can't give operational meaning to, it's been for a good reason. It's because they don't actually make sense. They're not fundamental ideas. Just like we had the uncertainty principle that says we couldn't talk about positions and velocities, even though in the Newtonian world you could talk about positions and velocities. This is telling us we can't talk about space and time when we start exploring distances shorter than 10 to the minus 43 seconds, 10 to the minus 33 centimeters. That means space-time is doomed. Okay? Space-time cannot fundamentally make sense. So once again, just as the classical physicists struggling with quantum mechanics didn't know what physics was supposed to be about, because wasn't physics about predicting positions and velocities, and what if there are no positions and velocities? So we are in a similar bind. Physics continues to be about predicting things that happen in space and in time. The words space and time are interwoven into what even physics is supposed to be about, and yet we know that those concepts cannot fundamentally make sense. These issues become important in a variety of settings. For instance, you all know that the universe is expanding, and if we run the picture of that expansion back in time, at some point the universe is very small, hot, dense, et cetera, and we call that place a Big Bang. Now, often people ask, what came before the Big Bang? No, you scientists don't know anything. What came before the Big Bang? Okay? Well, in fact, we don't know what happened at the Big Bang. But one thing that we know for sure is that the whole ideas of space and time are breaking down. So the whole question, what came before, the word before in that question, may not even make sense. That's a place where we need whatever replaces space and time. We don't have it, which is why we can't answer the question. But it's unlikely to have a simplistic answer like, oh, and before the Big Bang, everyone was happy. You know, it's very different things are going to happen there. Similarly, at the center of a black hole, which is another place where things get infinitely crushed down to tiny distances, our theories simply break down when gravity and quantum mechanics both become important. Full stop. Now, this is a subject that string theory was supposed to say something about. And string theory, pre-1995, started with the premise that a way around this problem was to say that all the particles that we know of aren't point-light, but at sufficiently small distances, we see that they're little strings. And in fact, the idea was that they're little strings around 10 to the minus 31 centimeters big. That's advised, not 10 to the minus 33, 10 to the minus 31 centimeters big. And the idea was that when they're 10 to the minus 31 centimeters big, this little problem with these Planckian black holes that I was talking about wasn't as severe, because that little black hole couldn't swallow up the whole string. String theory also forced there to exist extra dimensions of space, a total of 10 dimensions, with 6 of them curled up to tiny sizes, also around 10 to the minus 31 centimeters big. But something very interesting happened around 1995, which is that whatever string theory is, it's realized not to be a theory of strings. So unlike what you might read in Brian Greene's book or whatever, the big deal is not that everything goes from being a point to a little loop. In fact, string theory contains all kinds of objects, points, strings, even higher dimensional objects, membranes. And the upshot, this is again a topic for its own talk, but the upshot of these developments is that a while before everything was restricted to being around 10 to the minus 31 centimeters, really strings in extra dimensions can have any size with these new ingredients. And it's an experimental question what sizes they actually have. Finally, this whole dichotomy between particles and strings has disappeared. This has been probably the most important theoretical development of the last 20 years, is that we realize it's not particle theories or string theories, but that in fact particle theories and string theories can be different facets of exactly the same thing. Again, unification at a very, very surprising way. Okay. I won't have time to talk about this if I'm going to talk about anything else, so I'll skip saying about it. talking about it in any detail, other than to say it gives our first hint of what the idea of emergent space might actually look like. A more disturbing recent realization is that while string theory is unique in the sense of having no adjustable parameters, it has zillions of solutions. And a solution of a string theory is some, at long distances, looks like some universe that has some particles and some forces in it. At a fundamental level, they're all part of the same package. Everything's made out of the same stuff. But one solution might have a world that looks like it has 10 kinds of electron, 2 kinds of photon. Another world might have something that looks like it has 3 kinds of muon, 4 kinds of strong force. They all have gravity. They're all unified. They're all part of exactly the same theory, but there's lots and lots of solutions. Now, pre-1995, people thought that zillions meant millions, and that millions might be whittled down to 1 when we understood the theory better. What happened was exactly the opposite. Post-1995, we understand that zillions means zillions. It means 10 to the thousandth, okay? And that number is, uncertain in the exponent by a lot, okay? But we know it's many, many. And just to calibrate that number, the number of atoms in our universe is 10 to the 80. Okay, so when we say there's 10 to the 1,000 solutions, that's really quite a lot. What's remarkable is that these are all part of the same theory. In fact, it's a unification in an even more amazing sense than you would have thought possible. Not only could all of our forces and interactions be unified in some underlying theory, but incredibly different kinds of universes could also have exactly the same sort of description, be made out of the same sort of stuff. So this set of huge number of possibilities is known as the string landscape and is a very controversial subject. It's a controversial subject for obvious reasons, because many people, certainly many of my colleagues, don't like to think of our universe as being not unique. If our universe isn't unique, it's probably not that special. If it's not that special, what are we doing studying it? That's one reason it bothers them. It doesn't bother me. This picture suggests that the universe on enormously large scales is sort of an infinite fractal. It's really kind of mind-boggling. That the universe around us looks pretty homogeneous as we look around. It's not too different from place to place. But on really huge scales, if you imagine being able to zoom way back, the idea is that it looks very, very inhomogeneous, very lumpy. That there are all kinds of different regions in this bigger multiverse. Again, they're all connected. Everything's connected. Everything's part of the same theory. But in this giant multiverse, there are regions here where there are 12 kinds of electron. Here there's no strong force. Here it's actually 10-dimensional. And maybe we're a little droplet in this enormous multiverse. That's at least a picture which is suggested by these developments. But as you can tell, that's often in popular talks you give little pictures, and really it's a vast simplification of something that has lots of well-defined mathematical machinery underneath it. This is really the state of the art in this subject right now. But I say that partially jokingly because, but it's serious. This is the serious question is, how do we figure out how our particular solution, our particular vacuum is chosen? It's clearly that there's no sense in asking what fraction of this big multiverse is of one kind or another, as one solution or the other, because any way you count it, you get infinity divided by infinity. That, as Mr. Ledger taught me, is anything you want. Okay. So we're clearly missing something very, very big in understanding very, very basic things that is forced on us by this picture. In order to make progress, we have to understand both quantum mechanics and cosmology simultaneously in order to take the next step. This is certain to involve the idea of emergent time. I told you that space and time can't be fundamental. So everything about cosmology, everything about this whole zooming out picture at late time, seeing the universe has got all these bubbles, necessitates understanding the notion of time in a more fundamental way. So this is really an active area of current research. So we hope to take those little balloony pictures and turn them into more solid, concrete mathematics, and it's what a lot of people are working on. But what's at stake is clearly an enormous shift in our understanding of our place in the universe. Okay? Our entire universe could be this minuscule, tiny speck of nothing in this giant multiverse. So much for the mysteries of quantum gravity. Clearly, this business is in need of hints and help from experiment. And this is something I'll come back to a little later on. All right, so that was the first mystery. Let me turn to the other two mysteries that I talked about that had to do with taming this quantum mechanical vacuum. And again, the problem has to do with this basic issue in quantum mechanics we've been through a number of times. Because of the uncertainty principle, even the vacuum has energy. If you take a little box, in that little box there are all these virtual particles popping in and out all the time. As you make the box smaller and smaller, there's even bigger and bigger fluctuations of these virtual particles. So that if you just make a simple estimate for how much energy is there per volume in space, if I take a really tiny box of Planckian size, and I'll find there's Planckian energy in a box of Planckian size, that gives me a really enormous amount of energy per unit volume. Now, Einstein taught us that any energy gravitates. Any energy curves space-time. And in this case, this energy would curve space-time, and the typical scale of the curvature would be around the only scale we're talking about, 10 to the minus 33 centimeters. For example, that would lead to the universe accelerating, doubling in size every 10 to the minus 43 seconds. Okay, we just proved that wrong. In fact, the very biggest experimental discovery of the last 20 years has been the realization that the universe is accelerating. So it is. Our universe actually is accelerating. But it's not doubling in size every 10 to the minus 43 seconds. No, it's doubling in size every 10 to the 10 years, every 10 billion years. 10 to the minus 43 seconds is very different than 10 to the 10 years. So that means that the simplest explanation is that there is some vacuum energy, and that its size that we actually observe is around 10 to the minus 120 times that little estimate that we did in the previous transparency. Okay, so this is the biggest error in the history of physics. It's the biggest disagreement between the back of the envelope estimate and reality ever. And I want to remind you, what's at stake here is, why is the universe big and flat? We're not asking a complicated question, some detailed question. Why do we have a big universe? Why aren't we doubling in size every 10 to the minus 43 seconds and being ripped to shreds? Okay. Now, that's a simple question. It would be nice to have a nice answer to that. But here's our answer. What we do is we do the following. It's called fine-tuning for reasons that'll be obvious. We say, oh, okay. That's just one piece of the vacuum energy coming from these quantum stuff. And let's say you calculate to some, as accurately as you want, and you calculate. You say, what it is 2.649378. You keep going to 114 decimal places, 53, ... Okay? And then you say, so there must be, on top of that, just a classical piece for this energy per unit volume. That's negative 2.649378, blah, blah, blah. They agree to the 112th decimal place, and they disagree in the 113th decimal place. So we just pick that number by hand and adjust it to the first 120 decimal places, okay? And then they just disagree in the 121st decimal place. I'm allowed to do this. Nothing stops me from doing this. But you can see why it's called fine-tuning. And you can also see why it's completely nuts, right? This is ludicrous. An analogy that's helpful is to think that it's like walking into a room. Suppose you walk into a room, and you see that there's a pencil that's standing vertically on its tip to an accuracy of 10 to the minus 120 degrees. That's possible. You know, someone could have adjusted it. That's a correct solution of the equations. But that's what it's like. If you saw this, though, you might think there's something else going on. Okay? But that's what we do. And again, I want to stress that if this didn't happen, we wouldn't exist. Nothing would exist. The entire universe would just be blown apart by this rapid expansion and would be totally empty. As it turns out, interestingly, there's a virtually identical problem with the origin of mass in the Standard Model. So remember I told you that the electron moves along and bangs into this background condensate every 10 to the minus 17 centimeters? Well, that condensate is fluctuating like crazy like this as well. And those fluctuations are so violent, these quantum fluctuations are so violent, that the estimated distance between these collisions would be like 10 to the minus 33 centimeters, and not 10 to the minus 17 centimeters. So the observed fact that it's really 10 to the minus 17 centimeters, again, needs a fine-tuning of the parameters of the theory to an accuracy of 1 part in 10 to the 30. It's not as bad as 1 part in 10 to the 120. It's still like winning the lottery many, 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 many times. Okay? Incredibly unlikely for it to just happen accidentally. If this didn't happen, we wouldn't exist. And in fact, this is associated with another simple question. Why is gravity so weak compared to all the other forces? You would like to have a nice answer to that question, and this is our answer. So this spectacularly successful theory that we have has buried in it this skeleton, that in order for everything to work, you have to adjust 2 parameters, one to an accuracy of 1 part in 10 to the 120, the other to an accuracy of 1 part in 10 to the 30. And if that sort of tuning didn't happen, instead of having this nice big separation of scales between the 3 fundamental distances we've been talking about, they would all be collapsed on top of each other. This would be a very unpleasant universe, needless to say. Not only would everything be doubling every 10 to the minus 43 seconds, but you and I would also all be black holes. Okay? So that's the question. What controls these violent fluctuations of the vacuum? Okay? So here's a summary again of the crises, and then I'm going to just spend a few minutes telling you about some of the ideas for resolving them. At the Planck scale, we saw that space-time has to be doomed. And these very gross features of our world seem to require us to do ludicrous things to the parameters of our theory. Okay? We're not talking about problems that involve some disagreement between theory and experiment in the 6th decimal place of some detailed, obscure calculation nobody cares about. We're talking about very, very basic things about the gross properties of our universe. The LHC will definitely shed light on one of these questions. And if we're very lucky, it might actually illuminate all of them. Remember that the LHC will definitely probe the Higgs, the excitations of the condensate. And if something is responsible for taming the Higgs's violent vacuum fluctuations, the LHC must see it. And you see, it's not just revealing some random set of new particles. It's got to reveal some new principle of nature. So what might it be? Well, morally, if I go back to this picture of the pencil standing on its tip, it's like saying, instead of someone just putting it there, that maybe if you look at short enough distances, you see that there's a little hand holding it up. Okay? So there's something stabilizing it. Okay? There's a reason why it so appears finely adjusted. It only appears finely adjusted. It isn't really finely adjusted. There's something that's holding it. So for the past 30 years, people have tried to come up with different ideas for what such hands might be. And it's not so easy. It's not so easy to come up with extensions of the standard model, extensions of our laws of nature that don't disagree with things that we already know and which solve some of these problems. So in this 30-year period, maybe 2 or 3 kinds of ideas have been devised for what these hands might look like. And interestingly, all of these ideas involve new extensions of our ideas of space-time in one way or the other. The most theoretically appealing idea that a lot of people like really is a repetition of one of the stories I told you of going from ordinary matter to matter and antimatter. Remember I told you that when we had quantum mechanics and special relativity, we were forced to include antiparticles. And those antiparticles solved one of these ancient classical conundrums for why the electron had infinite energy. Why it didn't have infinite energy. That if you went to short enough distances, you actually saw that there are all these partners of all ordinary matter, these antimatter particles, and these got rid of the problem. Similarly, there's an extension now even of the ideas of special relativity. there's an extension to our notion of space-time that actually incorporates quantum mechanics, importantly, in the description of space-time. In a sense, new kinds of quantum mechanical dimensions, which is known as supersymmetry. And supersymmetry is really almost exactly analogous. Just like antimatter further doubled the world and solved one of these problems involving huge, enormous fluctuations, similarly, supersymmetry further doubles the world and amazingly solves this Higgs problem. So if this is true, the other half of the world is waiting for us at the LHC. If supersymmetry is discovered at the LHC, the title in the Globe and Mail or the New York Times will be "The Other Half of the World Discovered at Accelerator in Geneva." Europeans are very happy. Yeah. Americans aren't so happy. Now, it's hard to do this subject justice, especially in a very few minutes, but I just want to even give you a rough flavor of what it's like. See, imagine our ordinary dimensions of space. We have this direction and that direction, but if we have an electron wandering in this direction, an electron wandering in that direction, we still call them both electrons, because there's really nothing that special about this direction of space versus that direction of space. There's a symmetry between the properties of the electron moving this way and that way. They have the same mass, they have the same charge, they're still electrons, they're just moving in another way. The idea of supersymmetry adds to our ordinary dimensions of space-time, as I say, new sorts of quantum dimensions. And now, when the electron is wandering around in those quantum dimensions, it appears to us not as an electron, but as a new kind of particle called the superpartner of the electron, or the selectron. Okay? And that means that there's some interaction between, for example, electrons and photons. Well, because selectrons are really electrons just moving in the orthogonal quantum dimensions, there is a similar interaction between selectrons, electrons, and the photino, the superpartner of the photon. Okay. And these interactions are just such that, because of this magic symmetry, they remove this big, violent quantum fluctuations that I was talking about earlier. If these ideas are right, these supersymmetric particles must show up at the LHC. So we just really have to see that for each and every one of these particles, there is some superpartner, and we have to see them. One of the reasons people are so excited about supersymmetry is that if you introduce supersymmetry at 10 to the minus 17 centimeters to solve this problem, motivated by this problem, then something remarkable happens that just falls in your lap without wanting to do anything. I told you that the standard model gives you a unified description of the strong, weak, and electromagnetic forces. It's true they have a similar kind of description, but they're not identical. For example, the strengths of the particles the strengths of those forces aren't identical. But the rules of quantum mechanics and special relativity allow you to see that actually the strength of those interactions depends very, very weakly, but somewhat, on distance scale. So the strong force gets a little weaker as you go to short distances. Electromagnetism gets a little stronger as you go to short distances. And there's well-defined rules for how to calculate what the strengths are. With these superparticles, at 10 to the minus 17 centimeters, using these rules, you find that the strengths of the strong, weak, and electromagnetic forces all unify and become one at around 10 to the minus 30 centimeters. These three lines cross at a point. They didn't have to cross at a point. This very strongly suggests that there is some kind of unified theory of all of these interactions, because at these distances, they have identical strengths, and this picture doesn't do it justice. This is a near head-on collision of these three lines. Furthermore, this 10 to the minus 30 centimeter scale is very, very close to the 10 to the minus 33 centimeter scale I was telling you about earlier. That's where gravity becomes important. So there really seems to be some direct hint of some kind of unification of all the interactions taking place at very short distances. Einstein struggled for the last 30 years of his life to find a unified theory with no success. Again, in physics, when you're on the right track, good things happen when you don't try. This is a wonderful thing that happened that didn't have to happen, which really seems to suggest that there is something to the picture of supersymmetric unification. Now, what will this look like at the LHC? Again, unfortunately, you don't just turn the LHC on and particles come out and say, hey, I'm a superpartner. What happens is you collide the protons. There's the POW region. and you'll produce some of these supersymmetric particles. Really, it's because there's two quarks, they bang into each other, and now they just find themselves moving in the quantum dimensions. They were moving in the ordinary dimensions, they get shaken up, and now they move in the quantum dimensions. The quarks turn into squarks. I'm sorry, don't blame me for the names. Blame my intellectual ancestors, okay? Everyone was weird in the 60s. So this squark moves along, and this squark, as I told you, these things don't last long. This decays in around 10 to the minus 27 seconds into a quark and a photino. This squark on the other side can decay to a quark and then a WeNO, and the WeNO can decay to an electron and this electron can decay to an electron and a photino. The photino totally escapes detection. It's very weakly interacting. It just plows through the detector. Nobody notices it. What you notice are these electrons and quarks. That's what you measure. And there's scores of diagrams like this, scores of processes like this. And from measuring the detailed properties of the directions and energies and all kinds of other stuff of how these particles come out, we have to try to reconstruct that this is actually what happened. Okay? There's another possibility for what we might see at the LHC that again involves an extension to our notions of space-time, which is we might even see the effects of strings and quantum gravity at the LHC. I told you before that after 95, strings could have any size, extra dimensions could have any size, and one possibility is that the strings themselves are around 10 to the minus 17 centimeters big, and that gravity just looks weak because gravity spreads itself out in some of these extra dimensions that are larger than we thought before, while the other forces, me, quarks, photons, are stuck to living on a three-dimensional membrane that floats in this higher dimensional space. That's an exotic but completely allowed possibility from everything we know experimentally. And if this scenario is realized in nature, then the LHC will be a machine to probe quantum gravity. So we could smash protons into each other and dump energy into the extra dimensions in the form of gravitons. Or we could smash protons together and see that things are made out of strings. Or we could smash protons together and see that we make little microscopic black holes. All of these processes have very, very distinctive signatures in these detectors. And again, if you know how to look and you train yourself to look, you can see them. So I want to stress all of these ideas have concrete experimental predictions that we will probe very soon. A last thing, the final thing, is that there's a completely different sort of possible explanation for the fine-tunings that we're talking about, that I just talked about. It could be that there isn't some little hand that's holding it up. It could really be an accident. It could really be an accident that these parameters are finely balanced against each other to very high accuracy. But it's a sort of accident that we're used to happening in our world. For example, we know the Earth goes around the sun at a pretty nice distance. If it was closer in or further out, we'd boil and die or freeze and die. Okay? Or we know that we live on the Earth rather than in empty space. Well, that's an awfully tiny amount of volume to be living in the whole universe. So why do we live on the Earth rather than empty space? In both of these cases, it's not too surprising. There's, in our universe, lots and lots of different sorts of environments. There are lots and lots of other planets, lots and lots of other galaxies. Most of them are too hot, most of them are too cold. And in a few Goldilocks places, it's just right. Okay? And of course, we're going to find ourselves there, because there are zillions of other places we could be. Most of them are empty. We're in the place where it's not empty. This is a sort of obvious reasoning in our own universe, but it becomes interesting if you combine it with the idea I told you earlier that's suggested by string theory, that we might actually be part of a vast multiverse. See, if we're part of a vast multiverse, then maybe way out there, as you zoom out, you find that, yeah, gee, there are lots and lots of other universes, and these other universes, the parameters have very, very different values. Most of them, this nice cancellation between the classical and quantum contributions to the energy density of the vacuum don't happen. So in most of them, here it's doubling in size every 10 to the minus 43 seconds. There it is, tons of places. It's just exploding out. But there's so many of these places that just accidentally, in a few of them, it won't be doubling in size every 10 to the minus 43 seconds. And of course, we're not going to find ourselves in the place where it is doubling in size every 10 to the minus 43 seconds. We're going to find in places that allow us to exist, that allow structure to exist. And in this picture, again, you might imagine all kinds of different places we could be. Most of them are terrible, but in just a very few of them, accidentally, the properties are such that we can be there. Everywhere else in the universe is lethal. In the multiverse is lethal. A few places allow us to exist. This is a very bleak picture of the universe, but it's one that's certainly suggested. And if this picture is true, it's really the modern Copernican revolution. I think it would go down as the biggest discovery of our time, but we're still struggling to both make mathematical sense of it and even conceptual sense of it. We can't yet see the other universes. We don't know how to build telescopes to see them, like we can build telescopes to see the other planets, or at least other galaxies. But in the meanwhile, is it possible that the LHC could weigh in on this question? Are we a tiny part of a vast multiverse? And it's actually conceivable that it could. I don't really have time to explain how that is, other than to tell you that there are certain sorts of theories that are completely bizarre from the usual point of view, but are very natural from the multiverse point of view. And the LHC might find evidence for theories like that would really leave us scratching our heads unless we believed that the multiverse existed. So while the LHC can't prove that the multiverse exists, it could certainly give us a big kick in that direction. Just to end that subject on a bleak note, if this picture is true, our universe will definitely have a catastrophic end, okay? Because there are all sorts of places nearby where the energy is much, much lower, and by this phenomenon of quantum tunneling I told you about, our universe is going to last a very, very long time, but eventually we'll tunnel into a big crunch. Fortunately, we won't know what hit us, literally, because these bubbles of the other universe that's crunching us is moving out at the speed of light. So by the time it got your leg, your brain won't have time to react. Okay? Anyway, I want to end now. We've seen that many ideas of modern theoretical physics are on a collision course both with each other and with experiments. Hints from cosmology and the accelerating universe, problems of quantum gravity, the problems in particle physics and fine-tuning, as well as ideas from the string landscape. Some of them fit with each other, others don't. There's a jigsaw puzzle and the pieces aren't all fitting. And really, the last time tension about fundamental ideas was so high was the eve of the twin revolutions of relativity and quantum mechanics, at least in my estimation. So the stakes for the answers to these questions are very high. Well, what will the LHC tell us? I told you that it could either give us a new extension of our picture of space-time incorporating quantum dimensions. It could give us glimpses of quantum gravity, or in a completely different direction, it could give us a strong hint that we're part of a multiverse. These things are all very different from each other, and whatever it is will send physics careening in one direction or another, but we desperately need the hints from experiment to at least help us to proceed. So, it's kind of like Frodo in The Lord of the Rings. All of our hopes rest on that little ring. And you should really stay tuned, because the era of theoretical speculation in this business is really coming to an end. We should really have something solid to say by 2010. Thank you very much.
Thank you very much, Nima. We have a little bit of time for discussion and questions. I just wanted to comment that not only was that one of the broadest and most comprehensive talks we've ever had at Perimeter, it was the only one when nya 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 was actually used. So you're setting records all over the place. I do want to, I know some of you have some questions, and we only have a few minutes left, so I want to get to those, but I do have a few questions of my own that I think members of the audience would be interested in, and I'll start with the extremely obvious ones. You painted an extremely vivid picture of what we might see and what it might imply and entail. You didn't go out on a limb and tell us what we will see. And we have television cameras here. So I thought it would be appropriate to I guess, ask you two questions. On the record, what's going to happen at the LHC, and what are we going to see? And the second question is, what would cause you personally / professionally the most pain? In terms of what would be the most disappointing scenario when you turn the LHC on?
Do I get to use that? No, I guess I don't need to. I thought you were my friend. So I'm not going to answer your first question. I'll sort of answer it.
Okay.
I think if you asked people 10 years ago, they would have been much more certain about what was going to happen at the LHC. I think because 10 years ago, both the theoretical and the experimental situation were a lot less confusing than they are now. 10 years ago, I think 90% of people would say we will see some variety of supersymmetry, these quantum dimensions of space, because of this beautiful picture of unification and so on. A lot of things have happened in the intervening 10 years, data from cosmology, data from particle physics, that have clouded the picture significantly. Now, it depends what your attitude is towards these cloudings. And about half the time, I think we're just, half the time I think it will be that more or less standard picture from 10 years ago. And all these hints are red herrings, and you know, you could just stay the course, and this will be revealed basically as it was envisioned 10, 15 years ago. That's what I think half the time. The other half of the time, I think that we're going to get something much more radical than that. And it's really, you know, it's, I wake up one morning thinking, there's no way, you know, it'll just be some kind of supersymmetry, obviously. And the other half of the time, I think, no, maybe the multiverse is really right. Maybe we're going to see some hints for something like that. So I will go out on a limb and say I think something related to quantum dimensions of space will show up. It might not be the most vanilla, ordinary versions of supersymmetry, but I think, but there's something about those ideas that's kind of correct and is too nice to be completely an accident.
So you answered the question.
Oh, okay.
Yeah. All right.
That, however, you know, spans the entire set of possibilities.
Yeah,
that I told you. So it was a very Bushian answer.
Okay. We don't have, well, maybe I have time for one more question. So you made some allusions to this in your talk. This is not an essential part of what you were talking about, but I think it's interesting from maybe a more sociological perspective. So occasionally you were commenting on more speculative ideas that are out in the popular press, and a lack of appreciation, I think, for real knowledge and real understanding of where we are. So maybe, I'm not asking any specific question, but maybe you could elaborate on that a little bit.
Sure. I mean, it's one of the, I guess it's more a comment on what sells books, maybe, or magazine articles, or whatever. But it's really true that we've been in possession of this incredible theory for all the known interactions that work spectacularly well. We've been in possession of this theory for almost 30 years. And I think it's because we gave it a really boring name, the Standard Model. It doesn't quite capture its grandeur and scope. But it's important for people to realize, and that's part of the reason for talking a little bit about the history of these ideas, that one of the reasons why many of us are paid to make ridiculous-seeming speculations is that we have 400 years of experience on our side that say that such speculations have worked in the past over and over and over, and that seemingly crazy ideas are actually right. Of course, you know, not a random crazy idea is right, and that's why you spend umpteen years of your life in school. But still, we speculate, and the speculation is grounded in fact, and is grounded in experiment, and grounded in less tangible things, theoretical consistency, mathematical consistency, elegance, beauty. Things like that have guided us through 4 centuries of discoveries and have worked repeatedly in the past. And I think I really encourage everyone to learn something about the Standard Model. There's a wonderful popular book that just came out on the Standard Model. I think that's
we're going to be raffling that away, so stay tuned.
Right.
Don't leave.
Yeah, so that's just to see that the 40-year history of the development of these ideas, blind turns, wrong alleys, crazy ideas that ended up being right. Once you see that happen over and over again, that's why the rest of us speculate. We have a job to do, which is to answer the questions that we didn't even know how to ask before our intellectual ancestors cleared the road and brought us to such an amazing pinnacle to look out from.
Well, so given that, and given the exciting nature of the field right now, and the monumental times we're moving into, what advice might you give to somebody who is thinking about going into physics now? What advice would you give to somebody who was in Mr. Ledger's class or some equivalent right about now in terms of the future of theoretical, given that so much is uncertain, what would you recommend?
What I recommend that they do with their time, learn, study, work hard.
Is there anything in physics that you would?
No, I think the next 20, 30 years in fundamental physics, I focus talking about the Large Hadron Collider. There are also very exciting experiments coming up in cosmology that are going to teach us very complementary things about the universe. So these 2 fields, thinking about anything to do with gravity, quantum mechanics, cosmology, and the forces of nature, is going to be an exciting topic for the next 20, 30 years. So there's time. If you're just coming out of Mr. Ledger's class, there's time. If you're in kindergarten, we might figure it all out by the time you're done.
Okay, we have time for just 1 or 2 questions. There's a question right there. The gentleman right over there on the left side.
Progress toward the things that science fiction made us believe we see by now. So I'm wondering, when are we going to see more physicists working on cold fusion, or hot fusion for that matter, on anti-gravity, on time travel, and all those things that I would like to see some answers to before I pass away?
It's not wacky enough? I mean, I
No,
thought multiverses.
No, I mean, there's actually there's a good answer to your question, which is that the imagination of science fiction writers pales in comparison with nature's imagination. And what's actually true about the universe is far, far more mysterious, far more amazing, and goes beyond things that we could imagine in a more radical way than what our science fiction author friends can come up with. The ideas of quantum mechanics, the fact that determinism is wrong, the fact that antimatter exists, all of these things weren't even within the wildest imaginations of science fiction writers in 1899. So I think we're sort of content with understanding the universe as it is. Some of the things you mentioned, there are very good, well, fusion people are working on. It's a very, very hard problem. They may or may not make practical progress on it. Things like anti-gravity and time travel, there are very good physical reasons to believe that they're impossible. There are small loopholes that people explore. But it's really one of the very important things in physics is that really not everything goes. There are absolute limitations on things. And we haven't, completely 100% put the nail in the things that you're talking about. But we have, to the extent that many of us feel with the finite time we have available, that there are weirder and more interesting things that are probably actually true in the universe that are worth spending time on.
Indeed, and I think that's a great conclusion to all of this. I'd like to thank Professor Arkani-Hamed for a fantastic talk. Thank you very much.
Sorry it went so long. That's good. That was very good.